Alright, hello everybody. My name is Francis Walsh and my presentation is on the verification of high-speed digital interfaces. I may use this interchangeably with high-speed digital waveform capture, so please take note of that. So a little bit of background about me. I'm a Term 7 electrical engineering student. This was my 6th internship and my 5th co-op, and I completed it at Curtiss-Wright Defense Solutions. Curtiss-Wright Defense Solutions is a super old company dating back to the Wright brothers. They have locations all around the world, but the one that I worked at in the Ottawa location is focused primarily on developing electronics and avionics for vehicle defense platforms. So as you can see here on the top right hand corner, they create these circuit cards that slot into these vehicle platforms. So think tanks, planes, boats, and they do all the computation and controls for these vehicles. So in this presentation, I'm just going to go over why we do high-speed digital waveform capture, introduce the tools that we use for high-speed digital waveform capture, so that would be oscilloscopes. Then I'm going to review some course content from Engineering 1040 and 4430 because those some models from those courses are needed to select an oscilloscope correctly. And then finally, I had some real-world effects of probing a signal, but I may have to skip that depending on how we're doing for time. So just as a preface, I made some technical generalizations just due to the brevity of this time. And then the purpose of this is to kind of exemplify to the audience what goes into verifying a product before shipping it to a customer. So in terms of the problem context, imagine you're a hardware engineer at Curtiss-Wright. You've designed this product, you've sent it away, and then it got built, manufactured, you plugged it in, and everything worked as intended. But now, how do you verify that your product is going to work in an airplane at 40,000 feet at negative 30 degrees Celsius? So in order to verify that that will work, we use this process called design verification testing, or DVT for short. And digital waveform capture is a part of that. And so basically, it's a big part of it. And basically what we do as electronics engineers is we look at how every single microchip talks to every other microchip. So we look at how this interfaces with this, and how this interfaces with this, how this interfaces with this. And basically what that allows us to do is quantify the behavior of these circuits. And then once we've quantified the behavior, we can identify the marginal values of the circuit, as well as diagnose complex systems issues such as signal integrity, power integrity, and radio emissions. So generally an engineer or an intern like me would sit down with a card for about 4 months, go through it, and make sure that everything's working as intended. So bringing this back to Engineering 1040, I just want to tell you guys how information is conveyed electrically. So digital information is conveyed in binary, so ones and zeros. So if you remember Engineering 1040, electricity is composed of a voltage and a current, and that travels over resistance. And basically, when we're talking about digital waveforms, it's always encoded in voltage. So the voltage carries the binary from one chip to another chip. And so that's what this is here, a voltage waveform. And so the question is how do we view these voltage waveforms in order to quantify it? We use a tool called an oscilloscope. And basically, all an oscilloscope does is it captures these waveforms, these voltage waveforms, and then displays it over time. So as you can see here, this oscilloscope has a probe connected to it, and this probe is connected to a circuit that's under test. The electricity goes through the probe into the oscilloscope. There's a bunch of formatting and processing that's done, and then it's displayed on the screen. So when we're talking about high-speed digital waveform capture, we're talking about looking at things on timescales of pico and nanoseconds, so 10 to the negative 12, 10 to the negative 9. So we need to be very careful about that. Our tools, our oscilloscope that we use, can actually handle looking at timescales that small. So it's very important as an electronics engineer to have a very good understanding of the block diagram of an oscilloscope. And basically an oscilloscope is comprised of three major blocks. So once the electricity leaves the circuit that's being tested, it enters this thing called an analog front end. And what the analog front end does is it takes all of the noisy signal and turns it into a nice clean signal that we can take a look at. So here you can see on the bottom, this would be our input signal. You can see all of the noise, and then that gets filtered and creates this nice, beautiful, clean signal. Once the clean signal leaves the analog front end, it goes to the analog to digital converter, and what this does is it kind of takes a picture of the waveform in time, then converts it to a digital or a binary value, and is then sent to the microprocessor for processing. So a picture of that analog to digital conversion can be seen here. So this nice clean waveform is sampled, digitized, and then sent to the microprocessor. And the microprocessor then takes those digital values, stores it, and then displays it on the screen. So the question is now, how do we pick our oscilloscope for our high-speed digital waveform capture? And the answer is basically there's two main specifications that we need to look at. The first being the bandwidth of the analog front end. So that's the frequency at which the front end filters at, and then the sampling rate of the analog to digital converter. So basically how fast it takes that picture. So these values are generally on the front, on a nameplate of the oscilloscope. And so for this example here, this is the one that I own personally. This has an analog front end bandwidth, filtering bandwidth of 200 megahertz. So anything, it rejects anything, any frequency above 200 megahertz, and samples at about 1 gigasample per second. So 1 billion samples a second. Cool. So now, how do we select that analog front end bandwidth for our signal? So bringing this back to 4430, if you remember, a sum of sinusoids can represent a periodic signal, and that's called the Fourier series. And basically, on the right here, I'm just exemplifying, this graphic's just exemplifying that as you add more sinusoids, the fidelity of your wave or your represented periodic signal goes up. So in this scenario, we're representing a square wave. So what does this mean for digital waveform capture, and why do we need to use this model? So basically, this model is used to derive this rule of thumb that electronics engineers use to determine the analog front-end bandwidth, and that is the knee frequency. And basically, this is derived because when we're looking at a digital signal, we're only really concerned with the transition from 0 to 1. And we're not really concerned with what happens from at 0 or at 1. We're only care about the transitions, and that's just a fundamental concept of electronics. And so this knee frequency thing just tells us that we can retain 90% of the information or 90% of the integrity of this rising or falling edge at this frequency. So that's what this graphic is showing here. So the knee frequency, 90% of the energy is contained above or below that frequency. So we just plug all of our information from our signal into this knee frequency, and that'll spit out the analog bandwidth, the bandwidth that we need for the analog front end. So this is an example for a 100 megahertz square wave for a PCIe clock with a rise time of 0.3 nanoseconds. We're going to need a knee frequency or an analog front end bandwidth of 1.66 gigahertz to retain 90% of that information. And then finally, how do we pick our sampling rate? And this is really simple. We use a model called Nyquist's theorem, and all that states is that we need a sampling rate that's at least 2 times greater than the signal's knee frequency period. But generally, we try to do 10 times to retain the most information. And so this graphic is just showing that as you add more samples, the higher fidelity your reconstructed signal is going to be. And so for that example that I gave before, that was for that PCIe square wave, we need a minimum sampling rate of 3.2 gigasamples per second, since that's twice the analog front-end bandwidth that we need, which is the knee frequency. And so this is just an example of that waveform that we've been talking about. So the 100 megahertz PCIe clock, um, just showing that the bandwidth and the sampling rate that I used is much, much higher than the necessary knee frequency and sampling rate. And so you can see how this isn't quite a step response. It's only 90% of a step response, and that's because of that analog front-end bandwidth filtering. So just to recap, oscilloscopes are tools that display voltage over time. The bandwidth of the analog front end needs to be at least higher than the frequency, and the sampling rate should be at least 2 times the signal's knee frequency period. I had a bunch of other stuff, but unfortunately I'm almost out of time. So here's my references, and if you have any questions, I'd be more than happy to answer them. Thank you.